Let us discuss about Newton's divided difference interpolating polynomials. Okay, suppose we are given two data points. Okay, xo, f of xo, x1, f of x1. And we want to approximate the value of f at x. So say that is x, f of x. To approximate that value, the simplest form of interpolation is to connect these two data points. Alright? We connect these 2 points with a straight line. This technique is called linear interpolation. So at x equal to x, using linear interpolation, it will give us this value, x f of 1 x. Observe that there is a deviation which corresponds to the error e. By similar triangles, we have f of 1 x minus f of x of o all over x minus xo equal to f of x1 minus f of xo all over x1 minus xo. So we have this triangle. Okay, this triangle. So by similar triangle, f sub 1x minus f of xo is much is to x minus xo, as f of x1 minus f of xo is to x1 minus xo. So we can solve for f1x. That will be equal to, we cross multiply and then we transpose negative f of xo. So f of xo plus f of x1 minus f of xo all over x of 1 minus xo times x minus xo. This is the linear interpolation formula. The notation f1x indicates that this is a first order polynomial. The term f of x1 minus f of xo all over x1 minus xo is the finite difference approximation of the first derivative. So the smaller the interval between the data points, the better the approximation. Linear interpolation to a curve may introduce a significant error. So say for example, we have the points x sub o, f of x sub o, x sub 1, f of x sub 1. And then we want to find the approximation at x, f of x. Alright, this is x, this one is xo, this one is x of 1. So if we are going to interpolate our f of x using linear interpolation for the two given points, observe that it introduces significant error by this much. Alright? But if we are going to introduce some curvature into our data points, we can minimize the error between the approximated value and the actual value f of x. So in this case, we will be needing a third point. Let us call this as x sub 2. So that is f, or rather x sub 2, f of x sub 2. Alright, and we can fit here for these 3 points, xo, x1, and x2, a second degree polynomial. So we shall be connecting these 3 points, xo, x2, and x1. Let us denote this as by f sub 2x. This is the quadratic interpolating polynomial. Okay, a second order interpolating polynomial. And observe that in a way we have minimized the error between the computed value or the predicted value and the actual value f of x. For a more convenient form, we shall write our second order polynomial f2x as b sub o plus b sub 1 x minus x sub o plus b sub 2x minus x sub o times x minus x sub 1. So we have here the term x squared, indicative that that is a second order polynomial. Let us rewrite our quadratic interpolating polynomial f sub 2x equal to b sub o plus b sub 1 x minus x sub o plus b sub 2 x minus x sub o times x minus x sub 1. Okay, so we need to solve for the values of bo, b1, and b2. Let us set our x to x sub o. In this way, your x minus xo will become 0. So it will vanish the second term as well as the third term, since x minus x sub o will become 0. So what we have is f of 2 x sub o, or we just write it as f of x sub o, equal to bo. So that gives us the value of b sub o. Next, let us set x equal to x sub 1. By doing so, the third term will vanish as x minus x sub 1 will become 0. So we have f of 2x is f of x sub 1 equal to b sub o, which is f of x sub o, plus b1, your x is now x sub 1 minus x sub o. So solving for b1, that is f of x sub 1 minus f of x sub o divided by x1 minus xo. Alright, then we set x equal to x sub 2. So f of 2x becomes f of x2. bo is f of xo plus b1, f of x1 minus f of x sub o all over x1 minus xo multiplied by x minus xo. X minus xo, but your x there is equal to x sub 1. So x sub 1, no, it becomes x sub 2. X sub 2 minus x sub o. Because we have set x equal to, we have set x to x sub 2, so x minus x sub o becomes x2 minus x sub o. And then plus b sub 2 x minus xo is x2 minus x2 minus x sub o times x2 minus x sub 1. Alright, so solving for b2, we have f of x2 minus f of x sub o. Okay, transpose f of x sub o to the left side. And then minus f of x1 minus f of xo divided by x1 minus xo multiplied by x2 minus xo. And since we are solving for b sub 2, alright, we have transposed everything to the left, leaving b sub 2, x2 minus xo, x2 minus x1 at the right side. We divide everything by x sub 2 minus xo times x sub 2 minus x sub 1 divided by x sub 2 minus x sub o, x2 minus x sub 1. So we continue in the next slide. So the following slide provides us the simplification done on our equation in order to solve for b sub 2. So for f of x2 equal to f of x sub o plus f of x sub 1 minus f of x sub o all over x sub 1 minus x sub o times x sub 2 minus x sub o plus b2 times x2 minus xo times x2 minus x1. We transposed everything to the left except for b sub 2. So b sub 2 is equal to f of x sub 2 minus f of x sub 0 plus, so it becomes minus after transposing, that will be f of x1 minus f of xo all over x1 minus xo times x2 minus xo, everything divided by x sub 2 minus xo and x sub 2 minus x sub 1. So these are the manipulations done on the equation in order to simplify our b sub 2. We now write our b sub 2 equal to f of x2 minus f of x1 all over x2 minus x1 minus f of x sub 1 minus f of x sub o all over x1 minus xo, everything all over x2 minus x sub 0. We have also written our b sub 1 as f of x1 minus f of xo over x1 minus xo. b1 represents the slope of the line between xo and x sub 1. On the other hand, the expression f of x2 minus f of x1 all over x2 minus x1 is the slope of the line connecting x1 and x2. So for both these quantities, these are approximations of the derivative. And the entire b sub 2 is an approximation or a finite difference approximation of the second derivative. So we write our quadratic interpolating polynomial as f sub 2x, or simply f sub x equal to b sub o plus b sub 1 x minus x sub o plus b sub 2x minus x sub o times x minus x sub 1. From our discussion about the quadratic interpolating polynomial, we can now write the general form of Newton's interpolating polynomial. So for n plus 1 data points, our interpolating polynomial is f sub nx equal to b sub o plus b sub 1 times x minus x sub o plus b sub 2 times x minus x sub o times x minus x sub 1 plus and so on and so forth plus b sub n x minus x sub o times x minus x sub 1 and so on and so forth, times x minus x sub n minus 1, where the constants BO, B1 up to B sub n is equal to f of xo, f of x1, xo, B2 is f of x sub 2, x sub 1, x sub o, and so on and so forth, and B sub n is equal to f of x sub n, x sub n minus 1 up to x sub 1 and x sub o. These bracketed functions are finite divided differences. So for the finite divided differences, the first finite divided difference, f of x sub I, x sub j, is equal to f of x sub I minus f of x sub j all over x sub I minus x sub j. Say for example, we have f, the first divided difference, f of x sub 1 minus x sub o, that is equal to the difference f of x1 minus f of xo divided x sub 1 minus x sub o. Another is, say for example, f of x sub 4 and x sub 3. That is equivalent to f of x sub 4 minus f of x sub 3 all over x sub 4 minus x sub 3. Now for the second divided, or the second finite divided difference, f of x sub I, comma x sub j, comma x sub k, that will be equal to f of x sub I, comma x sub j minus f of x sub j, comma x sub k divided by x sub I minus x sub k. Actually, f of x sub I, comma x sub j is the first finite divided difference for the points x sub I and x sub j. And f of x sub j, comma x sub k is the first finite difference, divided difference between x sub j and x sub k. So similarly, so example for the second finite divided differences is f of x sub 2, comma x sub 1, comma x sub o, which is equal to f of x sub 2, comma x sub 1 minus f of x sub 1, comma x sub o divided by x sub 2 minus x sub 0. For the second finite difference, f of x5, comma x sub 4, x sub 3, it will be equal to the difference between the first divided differences, f of x sub 5, comma x sub 4, and f of x sub 4, comma x sub 3, divided by x sub 5 minus x sub 3. So in general, the nth final, or the nth finite difference, divided difference, denoted by f of x sub n, comma x sub n minus 1, comma and so on and so forth, comma x sub 1, comma x sub o, will be equal to the n minus first divided difference, f of x sub n, comma x sub n minus 1, comma and so on and so forth, comma x sub 1, and the n minus first divided differences, finite difference, f of x sub n minus 1, comma x sub n minus 2, and so on and so forth, x sub 1, comma x sub o, divided by the interval, or the length of the interval from xo to xn, which is x sub n minus x sub o. We shall now write the nth order interpolating polynomial f sub nx in terms of the finite divided differences is equal to f of x sub o plus the first finite difference, f of x sub 1, comma x sub o, multiplied by x minus xo, plus the second finite divided difference, f of x2, comma x1, comma xo, multiplied by x minus xo and x minus x sub 1, plus, continue, and so on and so forth, plus the nth finite divided difference, f of x sub n, comma x sub n minus 1, comma and so on and so forth, comma x sub o, multiplied by x minus xo, x minus x1, and so on and so forth, and x minus x sub n minus 1. This nth order interpolating polynomial is also referred to as Newton's divided difference interpolating polynomial. We work on the following example. We form the Newton polynomial of degree 3 for the following data points: 1, negative 1, 2, negative 17, 3, negative 59, and 4, negative 139. So we write our x sub o equal to 1 and f of xo equal to negative 1. X sub 1 is 2, f of x sub 1 is negative 17. X sub 2 is 3, of f of x sub 2 is negative 59, and x sub 3 equal to 4. F of x sub 3 is negative 139. So we start with our f of x sub o equal to negative 1. Then f of x sub 1 x sub o, that is f of x sub 1 minus f of x sub o divided by x sub 1 minus x sub o. That gives us negative 17 minus negative 1 all over 2 minus 1. That will be negative 16. Let us calculate also for x sub 2, x sub 1. That is f of x sub 2 minus f of x sub 1 all over x2 minus x1. That is negative 59 minus negative 17 over 3 minus 2, and that gives us negative 42. Then we proceed to f of x3, x2. That is f of x3 minus f of x2 all over x3 minus x2. F of x3 is negative 139. F of x2 is negative, so minus negative 59 all over 3 or 4 minus 3. That gives us negative 80. So the second, okay, the first, the second, we go to the third, finite difference, x sub 3 or x sub 2, x sub 1, x sub 0. Okay, that will be f of x sub 2 comma x sub 1 minus f of x sub 1 comma x sub 0 all over x2 minus x sub o. F of x2, x1 is negative 42. F of x1 comma x0 is negative 16, so that is positive 16 over x2 is 3 minus x sub 1. So that should give us negative 20. This will be negative 26 over 2, that is negative 13. We calculate also for f of x3, x2, and x1. That is f of x3, comma x2 minus f of x2, comma x1 all over x3 minus x1. F of x3, x2 is negative 80 minus f of x2, x1 is negative, so that is positive 42 over x3 is 4 minus x1 is 2. So that is negative 38 over 2, negative 19. So finally, we solve for f of x3, x2, x1, xo. That should give us f of x3, x2, x1 minus f of x2, x1, x sub o all over x3 minus x sub o. So f of x3, x2, x1 is negative 19 minus f of x2, x1, xo is negative 13. So that becomes positive 13 over x3 is 4 minus x sub o 1. So that is negative 6 over 3 is negative 2. Alright? We now summarize the results of the computations we have done earlier. So for x sub o equal to 1, our f of x sub o is negative 1. With x sub 1 equal to 1, the first finite difference f of x1, x sub o is negative 16. For x sub 2 equal to 2, our second finite divided difference f of x2, x1, xo is negative 13. And for x sub 3 equal to 3, the fourth finite divided difference f of x3, x sub 2, x sub 1, x sub o is negative 2. So our nth order polynomial using Newton's interpolating polynomial is fx equal to f of x sub o plus f of x sub 1, x sub o times x minus x sub o plus the second finite divided difference f of x2, x1, xo times x minus xo times x minus x1. And finally, the fourth, the first, the second, and the third finite differences f of x3, x sub 2, x sub 1, x sub o multiplied by x minus xo times x minus x1 times x minus x2. We simply substitute the values of these finite differences and your xi's. We have f of x equal to negative 1 minus 16 times x minus 1 minus 13 times x minus 1, x minus 2 minus 2 times x minus 1 times x minus 2, x minus 3. And so we have the third order polynomial, a cubic for f of x equal to 1 plus x minus x squared minus 2x. And we obtain this by simplifying the last line for f of x. So thank you for listening.